I gave a talk on tensor methods at the Bay Area Strata conference, and I'm happy to be back here. And so this is Tensor 2.0. So I want to give a general idea of the algorithmic side of machine learning. So most machine learning problems are non-convex. So if you run local search methods such as gradient descent, they tend to get stuck in spurious local optima. Right? So you need a lot of restarts to try to get to a good globally optimal solution. Today I'll show that using tensor factorization techniques, we can beat these perils of non-convexity. We can in fact go to globally optimal solutions with guarantees, and these methods are also computationally very efficient, parallelizable, and you can run this on a large scale. So I'll give both these ideas of how to analyze non-convex problems with tensor methods and how to deploy them in practical settings. So the newest part of this is how to use them to train neural networks, and that's joint work with my students Majid and Hani. So learning with big data is literally finding a needle in a haystack. Right? You have lots of data and the useful information is hidden within it. So I formulate big data as really learning a hidden low dimensional structure in high dimensional data. So as you have more data, you also have more variables or unknowns, and that's what makes learning with big data a ill-posed problem. And this is a challenging problem both statistically and computationally. So the statistical challenge is, in general, you may need lots and lots of data samples to be able to estimate the model. And the computational challenge, as I said, is the non-convexity. In general, you may need a lot of restarts to get to the globally optimal solution for general non-convex problems. And in this talk, I'll show how to deal with both these challenges using this paradigm of tensor algebra. So indeed, if you think about all popular machine learning challenges, they are optimization problems in most settings. So you can think of unsupervised learning, clustering, you can formulate it as maximizing modularity or a similar score, where you want to maximize similarity within the cluster and minimize similarity across the clusters. The maximum likelihood estimator for any probabilistic model, again, is maximizing likelihood. Dave Bly talked about topic models, so those are the special class of probabilistic models. Again, in supervised learning, you want to optimize certain loss function of being able to predict the labels correctly. So you can formulate all these problems, but they are all non-convex. And that's what makes learning hard. So with respect to our understanding of optimization, by now we have a pretty good handle on convex optimization. Whereas, the hidden part of the iceberg is really the non-convex part, right? So this is where our understanding is really lacking. And as I said, all these real-world machine learning problems are non-convex with lots of peaks and valleys. So how do we get around this problem of non-convexity? So with convex optimization, we have a nice property that there's only this unique optimal point, which is both global and local. So if you ran a local search method such as gradient descent, you know that you'll be making progress towards this unique optimal point. On the other hand, the non-convex optimization is a mess, right? So you can have lots of local optima. In fact, as you have more variables, there is curse of dimensionality. The number of spurious local optima can explode and become exponential in the dimension. And this is what makes large-scale learning very challenging. And we'll see how to deal with this problem of non-convexity by casting them as tensor factorization problems, and we'll be utilizing nice properties of tensor algebra to show that we can still converge to globally optimal solution despite having a non-convex problem. So I'll show this mainly in the context of neural networks, and in the previous set of things, we had looked at unsupervised learning of latent variable models, but now we'll see how we can solve neural networks using tensor methods. So indeed, neural networks have had a tremendous practical impact recently, especially in computer vision. And you know, on the algorithmic side, in fact, it's very simple, right? The backpropagation or stochastic gradient descent is just, you know, making local progress on the loss function. So given this practical impact, you know, we can step back and ask, what is the theory behind it? Can we analyze these neural networks even in very simple scenarios? So is there a problem of spurious local optima for backpropagation even in simple networks? So I'll start with a very simple toy example. This is just two-dimensional input data, and you see here these data points. This is the positive labels, these are the negative labels here. So it's a very simple, well-separated set of data points, and then we want to train a two-layer neural network, again with just two neurons, you know, very simple network, and ask, at least in this simple setting, does backprop not suffer from spurious local optima? Can we expect, you know, having globally optimal solutions in this case? It turns out, indeed, you know, you can think of the globally optimal solution as separating all these clusters with positive label with the negative one, right? So in this case, you do not incur any loss in predicting the labels of the cluster points. On the other hand, it turns out, even in the simple example, there is a spurious local optima. So there is a locally optimal solution that ends up classifying the clusters along these lines, meaning that it classifies this entire middle cluster as a negative label. So if you initialized anywhere close to this spurious local optima, you can get stuck in this bad solution. So you see that this problem of local optima occurs even in very simple instances for backprop. And you can visualize a projection of the loss surface of the parameters to see that. So if you look at the backprop cost function, you can see that there is, you know, bad non-convex case here, like you can get stuck in this region and not be able to make progress to the global optimal solution. On the other hand, I'll now demonstrate a new technique which does not suffer from this problem. Just to show the corresponding plot of the projection of the cost surface, you can see that it's a nice locally convex function here for our method. So how do we go about this? So what we'll do is we won't optimize on the original quadratic loss function that backprop does, and instead come up with a new objective function that involves factorizing a specific kind of tensor. And this allows us to overcome the problem of spurious local optima in a very general setting with neural networks. So let's see how to go about doing this. So training a neural network in general is NP hard, meaning there are hard instances for training networks. Right? So how do we get around this hardness? So the crucial insight we utilize is the knowledge of the input distribution. So the idea is, if I'm able to have a probabilistic model and learn a probabilistic model on the input, that will give me crucial information in also being able to train the neural network efficiently using a computationally efficient technique. And this is the classical debate between generative models and discriminative models. The neural network is a discriminative model, meaning that we are just learning the conditional distribution of the output or the label y given the input, right? But on the other hand, a generative model would try to model both the input and the output, the joint distribution on the input and the output. And so the idea is, even for a discriminative task, even for training a neural network, what we'll show is having generative models is highly useful. So this also relates to the idea that, you know, pre-training using unlabeled samples has been shown to be useful if there is a scarcity in labeled samples. And in our framework, we'll show how generative models can make the computationally hard problem of training neural networks tractable. So how do we go about using the knowledge of the input distribution? So the idea is, instead of directly using the input X to train a network to learn the label Y, we'll transform the input. So we'll come up with certain transformations of the input data and then use that information to train the neural network. And the idea is this feature transform will depend on the input distribution. So the insight is, depending on how the input is modeled, we'll have a different transformation and adapt the learning algorithm based on that. So how do we use this transformed data to train neural networks? So this is where we propose an alternate technique based on method of moments. So the idea is, if you look at the relationships between the input and output, that should be giving you some information about which neural network would be efficient in classifying these samples. So the simplest moment you can think about is the cross moment, right? You can look at the input and look at the correlation with the output and ask, how is this useful? Will this give me some information about training a good neural network? And I can take this further and then look at higher order moments. I can look at the correlation of the second order moment of the input with the output and so on. And so the framework we look at are general transformations of this input function of the input, and then look at the correlation with the output and ask, what kind of information does it encode, and how can I resolve the parameters of the neural network by using this information. So they're both the challenges of identifiability, meaning using these moments, can I identify a network with good parameters, and the other is the computational challenge of being able to do this inversion of the moments, meaning inverting the moments to get the actual parameters that are efficient in practice. Right? So they're both the challenges. And so this is where we'll need the structure of tensors. So if you think about pairwise correlations, you can use a matrix to encode them. But higher order correlations require tensors. So they're generalization of matrices, and you can describe it in a very intuitive way. Just as in a matrix, you can encode pairwise correlations between all the indices of your data, you can use, for instance, this third order tensor, you can index again all the correlations between the data indices using the tensor. For instance, here I1, I2, I3 index of the tensor will give you the cross correlation between the corresponding indices of the data here x and the label here y. Right? And so this formulation of tensors allows us to encode higher order relationships in data. And we'll see that this is crucial for being able to train neural networks and a range of other models efficiently. We'll see that just pairwise correlations by themselves do not have enough information, and we need these higher order moments. And the crucial aspect is being able to still do this in a computationally efficient manner. That's what makes them practical and useful. So coming back to the training of neural networks, we can now think about moments that are tensors. So you can think about transformation of the input that in general could be a tensor or a higher order moment, and we can ask what kind of information does it possess, right? So what class of transformations of the input will be useful for training neural networks. And this is where we look at this class of score functions. So the score function is nothing but the gradient of the log of the input density function. So this has been a very popular notion in statistics. It's been used for a wide class of estimators in statistics, mainly shrinkage estimators and so on. So what is the idea here? The idea is by looking at the gradients of the density function, we can get an idea of where there is large variation in the input distribution. For instance, in this toy example, if you think about the data as being distributed along the Swiss roll, and the score function, you can represent it as a vector field. And you see that where there is larger variation in the data density, then you have the larger amplitude of the vector field. So these score functions encode variations in the input distribution. So we can use score functions in our framework and look at the correlation with the label and ask what information does it have. In fact, what we'll do is we've proposed a hierarchy of such relationships. So why stop at just the first order derivatives? We can look at higher order derivatives of our input data. So by looking at normalized higher order derivatives, which I'll call higher order score functions, we can now generate transformations of the input that are higher order tensors. So if you look at second order derivative, that becomes a matrix. The third order derivative is a tensor and so on. So in this way, we can construct a hierarchy of score functions that are increasingly higher order tensors. So how is this relevant for training neural networks? So we'll see this for the case of a two-layer neural network, right? So this is the input layer here. You have the middle hidden neuron layer where there are arbitrary sigmoidal transformations, and then you have the output here. And we'll assume that the output layer is a linear one in this case. So if I assume that the label is in fact generated from the neural network, which is called the realizable setting, then the formulation is this way, right? You can write down how the function is represented in terms of the parameters of the neural network. So these weights A1 are the weights of the first layer, this A2 are the weights of the second layer, and the B's are the biases. So you can formulate it this way and ask, in this setting, can I relate the moment to the parameters of this neural network? So the crucial result which we established to make this possible, make this analysis possible, is an extension of Stein's lemma. So where we show that if you look at the output label and look at the correlation with the score function of any order m, what we have access to are derivatives of the label function in expectation. And for this neural network, it turns out that these derivatives are very nicely related to the parameters. So for instance, if we look at the first order moment, meaning I'm looking at the cross correlation between my output label and the first order score function, you can establish that it's nothing but a combination, a weighted combination of the weight vectors. So you have these individual weight vectors of the first layer. So each column here represents the weight vector of one of the neurons here, right? All the weights coming into that neuron. And this first order moment gives me access to a linear combination of these weights. And indeed, by itself, it's not useful information, but because you've combined all these weights together. On the other hand, now let's look at the second order moment, which looks at the correlation with the second order score function. In this case, you have a linear combination of rank 1 components, where each rank 1 component corresponds to one weight vector, right? So you have these combinations of rank 1 components. Again, this is somewhat useful, but not completely, right? Because if you ask me, can I uniquely recover these weights from this matrix, in general, that's not the case. You can only recover it up to a linear transformation. And that is why we need higher order moments to enable this recovery. If I now go to third order moment, again it's a very similar structure, meaning that this third order moment has a decomposition where each rank 1 component corresponds to one weight vector. But it turns out with tensors, you can in fact recover this decomposition uniquely. And that's why these tensors are powerful. So with just matrices, you do not have enough information and enough algebraic constraints to recover the weight vectors. But by going to higher order tensors, we can uniquely recover these weights under some very simple non-degeneracy conditions. And that's the idea of using tensors and not just matrix methods. And in the paper, you'll look at the details. There are some other simple Fourier techniques to even recover other parameters in this network model. So the main idea is once we have the input, we'll do unsupervised learning and come up with estimates of the score function. For instance, the third order score function is a tensor. Then we'll correlate these score functions with the labels in my label data and construct these empirical moments. And then we'll do a low rank decomposition of these empirical moments, right, where the rank is equal to the number of neurons I want in my network. And each rank 1 component, I'll use them as weight vectors of the first layer. And then the other parameters can be estimated through Fourier techniques. And the strength of this method is we can utilize a number of powerful results on tensor decomposition, which guarantees on being able to get the correct decomposition, being able to get the globally optimal solution to solving the tensor problems. And that's what distinguishes it by, compared to backprop, right? The objective function of tensor factorization, we can analyze them and prove, convergence to globally optimal solutions. So in our paper, you can look at the details. You can prove a bound that even with finite number of samples, you can converge to a good solution. And this is a polynomial sample complexity in being able to recover the parameters of the neural network efficiently. And we can in fact generalize this to learning general functions. I mean, in general, you have a function that you want to learn, and that need not be generated by a neural network. And it turns out that we can also extend to that setting as long as the approximation error for the network of that architecture is small enough. As long as you're guaranteed existence of a network with small approximation error, which again can be shown using Fourier techniques from classical results of Baron, we can show that we can learn a neural network with efficient risk bounds. And so this is the main result that shows that you can learn a very general neural network with arbitrary sigmoidal functions and arbitrary input distributions by using tensor methods with very efficient sample and computational complexity. In fact, these tensor methods are embarrassingly parallel, so the parallel time complexity is exactly the same as backprop in this case. So this is what makes these methods both practical as well as theoretically efficient. So let me give you a brief overview of other exciting results on tensors that also can benefit from this analysis for non-convex problems. In my previous talk at Strata Bay Area, I talked in detail about learning probabilistic models. You can think of Gaussian mixtures, hidden Markov models, independent components, multi-view and topic models. Dave Black gave a very detailed review of topic models. All these different models, you can look at the higher order moments, and by factorizing higher order moments, we established that you can consistently learn the parameters of these models in an unsupervised way with polynomial sample and computational complexities. So we have another line of work that's looking at making these algorithms practical and scalable. In our NIPS paper that will appear in December, what we show is the use of randomized sketching for tensors to make them efficient even if it's a high order. So if you do naive computation, as you increase the order of the tensor, the computational complexity becomes exponential. But what we show is by creating sketches based on efficient randomized FFTs, you can make this very efficient. And you get like the best scaling, which is linear in the input dimension and the number of samples. And we have another project in collaboration with NVIDIA to create highly efficient libraries for tensor operations. So the strength of tensors is you can build upon all the highly optimized linear algebraic libraries. So Reza talked about BLAS, which is the class of very optimized linear algebraic operations. And this idea of extended BLAS can be used to make tensor operations efficient. In particular, these GEMs or generalized matrix multiplications, you can batch them, and this class of batch GEMs can be very useful in making tensor operations parallelized, and we can minimize data permutations and I/O calls. And this is what will distinguish it with some of the existing libraries for tensor operations. We also have a deployment of these tensor methods on Spark, and we hope to be releasing it very soon. The in-memory processing paradigm of Spark makes it ideal for tensor operations since they are iterative and easily parallelizable. To give you an idea, if we can do the tensor CP decomposition or the low rank decomposition that I showed using alternating least squares. So essentially you can fix two of the modes of the tensor here, say B and C, and you can update A, which becomes a least squares problem. But you can also use the algebraic structure of the tensors to make this least squares problem efficient. And you can then update the different rows of this matrix A independently under the Spark paradigm. And just a very preliminary result, if we run the New York Times corpus for topic modeling, we get a huge speed up in Spark compared to doing it on MapReduce, which is expected because MapReduce is not really suitable for highly iterative operations. And so we hope to be releasing this very soon as well. So we can handle tensors in a number of other scenarios. One of the interesting ones is convolutional models. If you think about computer vision and other domains, you have invariances such as shift invariance, right? You don't want redundancy of like shifted dictionary elements, for instance, in this model. And so if you want to solve this as tensor factorization, now we want to incorporate these shift invariances as into the factors of this tensor. So we'll be factorizing the tensor into low rank components and at the same time be incorporating the shift invariances from the convolutional model. And you can do this very efficiently and implicitly through FFT operations, and this makes them again highly parallelizable and scalable. And we've been now using this for a number of applications in vision and NLP, and I can talk to you about details later on. Another exciting application we've been looking at is reinforcement learning. So in reinforcement learning, you also have a dynamically changing environment. So this class of partially observable Markov decision processes are very challenging models to learn because you have a hidden state here. You do not directly observe the state, and based on the action you take, you're also changing the transition to the next states. And by utilizing these tensor methods, we can show logarithmic regret bounds, and these are some of the first theoretical results for reinforcement learning of POMDP models. So to conclude, what we see tensor methods as a new paradigm for training in a number of challenging scenarios. This involves neural networks, unsupervised learning of a range of latent variable models, reinforcement learning, and so on. And so this really gives us a way to handle non-convex optimization and still be able to give theoretical bounds on getting good solutions. At the same time, these are embarrassingly parallel operations. They can be scaled up on Spark as well as GPUs and other parallelized hardware systems. And I think there are a number of exciting problems in this area, in being able to come up with a unified framework for tractable non-convex optimization. And this is my excellent research group, and there are lots of resources on my website, including the podcast I gave with Ben Lorica that I think will give you a very nice overview on tensors. Thank you.